Thank you, Didier, and thanks to all of the organizers for giving me this opportunity to present this work. So today I'd like to talk about fractional Chern insulators, and maybe more specifically how we can use DMRG to help us in the design of experiments which can probe these phases experimentally. So this was a work that was done in collaboration with two colleagues, Nathan Goldman from Brussels and Julian Leonard from Harvard. And so the details are published in this paper, in this reference below. So fractional Chern insulators, so they are a strongly correlated quantum phase of matter, which is very similar to the fractional quantum Hall effect. So the fractional quantum Hall effect, as probably some of you know, is a phenomenon that arises when you have a two-dimensional electron gas, for example, a two-dimensional quantum gas that's subjected to a very large magnetic field at very low temperature. And what is observed is that there's a quantization of the Hall conductivity to these so-called Hall plateaus of Hall conductivity. And maybe more generally, one of the reasons why we're very interested in this phase is that it's the first experimental example of topological order, meaning a phase of matter whose excitations are anyons. So they are particles beyond fermions and bosons. They have a fractional charge, a fraction of the charge of the electron, and also fractional statistics. So, for example, for abelian anyons, when you switch their position, your wave function will acquire a phase, which is just a number, a complex number. And it may be even more interesting in the case of non-abelian anyons, the position of all anyons in the system is not enough to fully characterize the quantum state. There is a degeneracy, and this exchange process what it will do is a rotation within this degenerate manifold. So in this talk, I'm not going to talk about this exchange statistics specifically, but more about a different type of fractional quantum Hall state, which is called a fractional Chern insulator. And basically, this is a way of realizing the same phases, so phases in the same universality class, but without having to rely explicitly on the magnetic field. So here, these are phases that are based on a lattice. And this is the lattice itself, which will give some topological properties to the system. And so fractional Chern insulators can realize phases in the same universality class as the fractional quantum Hall effect, as I said, but they can also do more. For example, it's possible to trap excitation within the dislocation on a lattice. So they're also interesting in their own rights. So how do we find them? How do we realize them? So far we have a pretty good understanding of the microscopic emergence conditions of fractional Chern insulators, but we don't have a material where they emerge naturally. So it makes sense to design some platforms where we can control the microscopic parameters in order to engineer these fractional Chern insulator phases. And a very promising platform to do so is cold atom in optical lattices. So in optical lattices, experimentalists can trap very cold atoms in these lattices, which can take the form that they want with a tunneling strengths between different sites that can be tuned to a very high precision. They can also engineer artificial gauge field, which play the role of a magnetic field, and it's also possible to tune the interaction. So it's a very promising platform to realize many condensed matter phases, but fractional Chern insulators in particular. So my question here is, if experimentalists manage to do that, how are we going to be able to tell that they reached their goal? How are they going to detect these fractional Chern insulators in cold atoms. So the most natural quantity, the most natural observable to measure or to calculate for a numerical work such as mine is the Hall conductivity, because in fractional Chern insulators, similarly to fractional quantum Hall effect, the Hall conductivity is quantized to a fraction times E squared over h, the quantum of conductance. More specifically here, I'll be interested in phases that satisfy a Hall conductivity 1/2 times E squared over h. And this will be a phase of bosons, of strongly interacting bosons. So one of the big questions here is how to measure the Hall conductivity in cold atoms. This is something that's routinely done in solid states when you have transport experiments, but it's not really trivial to know how to do the same thing in cold atoms. And there's a second constraint that's very specific to these engineered quantum systems, such as cold atoms, which is that you may be dealing with a very small number of atoms. And this has to do with the challenge of preparing a state with topological order in cold atoms, because there's no, unlike solid state, there's no way to directly cool down your system to reach the ground state. But typically what you have to do is to follow a path in parameter space. So first prepare a phase that you know how to prepare, maybe a trivial phase such as a Mott insulator, and then adiabatically tune the parameters through a phase transition and towards your topologically ordered phase. And because you're going from a trivial to the topological phase, you have to have a phase transition in between, which means that in the thermodynamic limit, there will be a gap closing. But if the system is sufficiently small, then this gap will remain open, and you can be almost adiabatic when going through this phase transition. So right now, it's one of the main strategies to try and prepare a fractional Chern insulator by starting from very small ensembles of bosons, namely 2, 3, or 4 bosons. The problem here is that the Hall conductivity is it's quantized in the thermodynamic limit, but there's no reason why it should necessarily be quantized for small systems. So on top of my first question, which was how to extract the Hall conductivity in cold atom systems, I have a second question, which is this quantity even going to be a good signature for my phase? Is it going to be universal at all when I have a very small system? So in this talk, I will show how numerically, namely using DMRG, we can simulate some protocols to extract the Hall conductivity, protocols that can later be applied in cold atoms, and show what kind of information we get from these protocols, and whether there is something universal about this small ensemble of bosons, FCIs, fractional Chern insulators. So this is the outline of my talk. I'll talk first about the models that I'm using. So I'll talk about how fractional Chern insulators are realized in the Harper-Hofstadter-Hubbard model. And then I will talk about 2 different protocols to detect fractional Chern insulator. One is a static protocol. Both of them are based on density measurements, but one is static, based on the Streda formula, and the other one is Dynamical Protocol. So let me start by giving a little bit of background and explaining the models that I'm using. So the model that we are considering is the Harper-Hofstadter model on the square lattice. So you have a square lattice with hopping terms between nearest neighbors. And this hopping term have an amplitude that is j in the y direction and j exponential I y phi in the x direction. And this complex phase here makes sure that if a particle goes around the plaquettes of this lattice, then its wave function will pick up a phase phi So it's a way to take into account an effective magnetic field by just adding in the out-of-Bohm phase that that this particle would be feeling if there was a magnetic field. So in this model, when you consider a commensurate flux, meaning phi equals to 2 pi times a fraction, p over q, then you can define the magnetic unit cell. Indeed, the translations on the lattice do not commute anymore, but they commute if you enlarge the magnetic, if you enlarge the unit cell and use the magnetic unit cell. So, it will enclose q lattice sites, and that will have an integer flux 2 pi times q, meaning that it will have q bands. It will be a band model with q bands. And I'm looking specifically at this model because it was already realized in cold atoms. So far I'm only talking about the non-interacting parts. We will be using an interacting model, which I will explain later on. So the flux phi, it's a parameter of the model, and in the course of the talk, I will change it and I will consider different values of the flux. But just to give you an example, when this flux phi is equal to pi over 2, then you can define a magnetic unit cell with 4 sites, which means that you will obtain this band structure here once you diagonalize the Hamiltonian. So it's a band structure with 4 bands, with a band touching in the middle. And if I'm focusing on the lowest band, which is the red band in this plot, and this band has a Chern number equals to 1, meaning that if I had a fermionic model and I filled it up with a filling 1, meaning I completely fill up the lowest band, then I would have a whole conductivity equals to E squared over H, an integer whole conductivity. So that's it for the non-interacting part of the model. Now, here we're considering not just the Harper-Hofstadter model, but the Harper-Hofstadter-Hubbard model, meaning that I'm just adding this Hubbard U interaction to the model. And I'm going to be using bosons in the model, so it's an on-site Hubbard U. So this model, there's already numerical evidence for fractional Chern insulator in this model. So namely, if you tune the number of lattice sites and bosons in your system such that the filling fraction of the lowest band is equal to 1/2, and if the flux is low enough, then you will find evidence of a fractional Chern insulator. So I just want to be a little bit clear about what the filling fraction is. It's not the filling of the lattice, but really the filling of the lowest band. So it's the filling of the lattice, number of bosons divided by number of sites, times 2 pi over 5. So this numerical evidence, it comes from calculations in geometry without edges. So either on the torus using exact zonization, or also with DMRG on the infinite cylinder. And there's also some evidence, maybe somewhat more suggestive in system with edges. But typically, when you have edges and you don't have any periodic boundary conditions, it's harder. You don't typically calculate the whole conductivity because it would require the insertion of fluxes in the cylinder. At least that's the easiest way to do this calculation. So it's maybe a little bit of a difficulty for us because we wanted to be as realistic as possible. So we wanted to use the geometry with edges to test our protocols. And the other thing is in geometry with edges, typically because you have a topological system, you would expect chiral edge modes, but We will be using here a hard wall confinement, which is in line with some ongoing experiments. And in this hard wall, with this hard wall confinement, these edge modes are actually gapped out. So how to find a fractional Chern insulator in a small system with edges, and how to calculate the whole conductivity are were somewhat unexplored questions until now. So now I'm gonna show you more specifically which protocols we design and which protocols we have in mind to extract the whole conductivity in this model in view of identifying these fractional Chern insulator phases in geometry with edges. So the first protocol that we have in mind is based only on a static measurement of the density, the local density actually, so the density on each side. And it's based on the Streda formula, which tells you that if you have a gapped ground state, then the whole conductivity is given by the derivative of the density with respect to the magnetic field. Here, the magnetic field in our system is the flux. So that's why I'm writing 0 d phi. And I added some index bulk to keep in mind that this should be the density in the bulk of the system, because the whole conductivity is a bulk quantity. So what's the bulk density? So here is the geometry of the system we are using. So it's this lattice with well, in the result that I'm going to show you, it has 120 sites. So first, you can obtain the ground state of the Hofstadter-Hubbard model that I described in the previous slide through DMRG. And then once you have the ground states, you can calculate the local density, which is defined as written here. And this is this is a quantity that can be extracted from cold atom experiments using a quantum gas microscope. So it was important for us to only use technology that was already available in experiments. So that's the protocol we designed to be readily experiments. So here is the result that you get for a system of 10 hardcore bosons. So the large U limits of my Harper-Hofstadter-Hubbard model and 120 sites. So instead of showing you a 2D plot of the density, I'm showing you just a cut for different values of the flux. So you can see that the density changes when you change the value of the flux. But more generically, maybe there's it's not quite constant in the middle, but there are very few fluctuations in the middle, in the central region, but far more towards the edge of the system, as you can expect. So we are going to call the density in the bulk. What we are going to call the density in the bulk is the average of this density in a small central region of our system. And it's, as you can already see from these images, it's going to vary from one flux value to the next. And it's why it's completely distinct from the average density, which would just be the number of bosons divided by the number of sites, and which is a quantity that doesn't depend on the value of the flux on the lattice. So let me now do that for several values of the flux phi and use the Streda formula to extract the whole conductivity in this system. So again, I'm using DMRG for 10 hardcore bosons in 120 sites. And I'm calculating sigma h as the derivative of rho versus phi just by a finite difference. So I'm just calculating, calculating rho bulk for many values of phi. And so this is the result that we obtained. This is the whole conductivity as extracted from the Streda formula versus the flux in the Hofstadter model. And you see that there's a region here where you have a plateau of the whole conductivity, and this plateau happens to be very close to the quantized value 1/2, which is the value expected for this specific fractional Chern insulator. Even for this relatively small system. So it's important here that it's close to 1/2, but it's also important that it's quite robust, that you have many values of phi where you have this plateau, because it's a good indication of a phase which is really here and not just an artifact that your whole conductivity somehow goes through the value 1/2.
Cécile, I have a stupid question, but why don't you have any points in some region of phi on the right-hand side? There's a large region of phi where I don't see any points.
Yeah, that could be.
Maybe it's not important. Sorry.
I think. So I hope that I didn't mistakenly hide them. But I think it could also be that they happen to be negative because this is a region where it just fluctuates a lot. Robert fluctuates a lot, and but there's not a lot of consistency. Maybe you change phase. There's a lot of phase transitions and so on. And since you jump from one row to the other very quickly, you can have negative values every now and then.
Okay, thank you.
Okay, so this was the first protocol, and now I propose to explore a different possibility based on the Dynamical Protocol, which explore really the definition of what is the Hall effect by measuring the Hall drift of the atomic cloud under a constant force. So the idea is to first prepare your fractional Chern insulator in a small region. So here, this is the green box. And then apply a constant force to the system and monitor the center of mass of your atomic cloud as you do so. So more specifically, there's some intermediate time from 0 to tau ramp where we progressively release the atoms into a larger box, and at the same time ramp up the force. And then after this small regime, we hope to reach a stationary regime and keep the force constant. So the reason we do this, the reason why we embed this fractional Chern insulator inside a larger lattice is just so that once we add the force, we don't want to probe. We don't want the atomic cloud to basically bounce against the boundary of the system. We don't basically want the cloud not to see the edge of the system at all. So you need to make it large enough that for the times that you are considering, the system looks infinite to your small green fractional Chern insulator region. So then within linear response, you expect that the whole conductivity will be given by the density in the bulk, rho bulk, divided by the strength of the force times the velocity of the center of mass in the direction transverse. So what you have to do basically, it's again a density measurement, but as a function of time this time. So you want to monitor the position of the center of mass. So which I've shown here. So this is a numerical calculation where you see that after the ramp in this region, you reach a stationary regime where the velocity of the center of mass is constant. You have a linear slope, so this is a constant velocity. So you can extract it from this calculation and extract the whole conductivity from that. So we have simulated this whole drift protocol numerically. Again, this is using DMRG. So we first find the ground states for Harper bosons and do a numerical time evolution by applying the time evolution operator. And then we use this matrix product operator algorithm to actually implement this time evolution numerically. So here is again, here are the results for same system size as we did for the other protocol. And as you can see here, there's again a region of flux where the whole drift tells you that the whole conductivity is quantized. You have basically a plateau of the whole conductivity with a value very close to 1/2. And this region coincides with the region where you have already a plateau of the whole conductivity from the Streda formula.
So Cécile, you still have 5 minutes before, a little less than 5 minutes before questions.
Sounds good. I'm almost done. Thanks. So here is the same result again, and now I just wanted to show you what the same protocol looks like if instead of having 10 Harper bosons, you only have 4, which seems like a ridiculously small number, but somehow you still do get some plateau features in the whole drift. So here I have 3 different colors, 3 different curves, and those different curves correspond to an evaluation of the density in the bulk according to a different radius. So remember how I estimated the density in the bulk by averaging the density in this small region of radius R0. Now I can take different values of R0 and see if it makes a difference to my result. So it's a way of estimating the error bar associated with finite size effect in a sense. Well, not exactly associated with finite size effect, but more associated with edge effects, if you want. And the interesting thing is that by changing this value, it will change the value of the whole conductivity, but it won't change the fact that you have a plateau. So you're still able to probe this phase in a sense, even in quite small number of bosons, even the number of bosons that are currently targeted by experiments. Right, so I think I have already said this. We have this quasi-quantized whole conductivity for 10 bosons. For fewer bosons, it doesn't work as well, but we already have some nice features of a plateau. And this plateau coincides with boundaries of the fractional insulator phase, as we can extract from other signatures that I didn't show in the talk. So in conclusion, DMRG is a very practical tool to simulate protocols of interacting atoms in optical lattices. And I've showed you 2 ways that the whole conductivity could be measured from local density measurements. And even for quite small ensemble of atoms, it provides a nice signature that is almost quantized. So a quite nice signature of a fractional Chern insulator. So that's it. Thank you for your attention.